Hello everybody, welcome back to today's session on transformer self-attention. In the previous video we had covered positional encoding, and now we are going to cover the heart of the transformer mechanism, which is the self-attention or the scaled dot product attention. Let's say the first word has appeared. First word after embedding. One word, therefore it is 1 cross dm is the dimension. Dm stands for the D model dimension, which is the embedding dimension, because these words are nothing but the embedded representation. It goes through a neural network. Attention is all you need. In that paper you will see this has been termed as linear projection. Now, but actually it is going through a neural network. The relationship between neural network and the linear projection is basically matrix multiplication, and we had a video on this which is the second video in this series, named as matrix multiplication and the relationship between the linear projection, neural net, and etc. Watch this video if you have any confusion here. So this embedded vector now is linearly projected or actually passed through a neural network. You see that in order to do so, we keep the rows of the neural network as dm dimension, and the output of the neural network, which is dk, is a parameter which we can define, hyperparameter, and that will be the output size. So therefore, if we do a vector is multiplied with this matrix, we are going to get a result of dk is the output, right? Its dimension will be dk. So that's for one word. Fine. Now this is nothing but the learned representation of the word, right, which we are terming it as query or the queue. Now moving on to this one, for all other words, if it's not the only single word, but there are other words in the sequence going from word 1 to word t, right, t sequences. Now in that case, that t, once for all the t words, this is not going to be, the result is not going to be a single vector, but this result is going to be a matrix of t rows, and dk is the dimension of, right. Using the same word, we create two more neural network. One is for k, the key, and the values. So for each one of them we will have one such matrix produced. This QKV was very similar to what we had learned in Badenau attention or the Luong attention. We had a much elaborate discussion on this front, but now let's just quickly remember that Q is the query part, and K, key and values, as if it's a dictionary or say key value store, from where the query is asking for some key, and key is found, then it will retrieve the value and give it to you, right? So the output dimension for query and key both are dk, whereas for the value the dimension is dv. Now one such query from the output of the query matrix we are taking, we are then doing a dot product with all the values of the key. So let's take one of them, but since it is dk this side and the rows here is t, we have to do the transpose so that the dk matches with dk. So we do that transpose kt, q, kt. So q will be now dot product with the kt, and then that will produce a score. How it is happening? The same q is now dot product on this row 1, produce the S11 score. This q is now dot product with this, and then last one, which is the tth row, then producing the S1t. That's how for each of this row it is going to give you one scalar value, right? That's the dot product. If you have any doubt on this, you can go back to the first video, which is on dot product, right? On this series, the dot product was the first video. Now similarly for other queries, also will come into picture, but let's understand what does it mean. It means that for ith word, what is the score with respect to all other words? One word with respect to all other words, what is the score for them? That's what it means, right? moving forward. Now this one is now will be going through a softmax layer so that the score are converted into a weight, and that is what is our alpha weight. That's the target, right? Our attention score is converted into a attention weight. The weight will have similar meaning that this is the for ith word, what is the weight with respect to all other words. Now you see that the scores are not only taken as is, but the scores are actually divided by the dimension of the query or the dimension of the key. Why is so? So the paper explains this very well. The paper is explaining that basically there are two types of attention scoring. We had learned it. One was in the first one, attention, which we had learned through the Badnau attention, which is the additive attention, and the other one is the Luong attention, or the multiplicative attention, which is dot product based attention. The multiplicative attention in general works very well, faster, because it's a matrix multiplication. Therefore it can be done parallelly, and that's why it is faster and efficient. However, that is true when the decay value is small, but for very high decay value, okay, this is not true. This creates a problem, because this higher value, when it is very high value, then the softmax creates a problem. And what is the problem they are referring? They are saying that we suspect that large values of decay, the dot product grows large in magnitude, and pushing the softmax function into regions where it has extremely small gradients. What does it mean? Okay, it means that you can see this is the output of the softmax. If we have plotted a moderate number, for example -5 to 5 or -2.5 to 2.5, you see the curve, the slope is very evident, the slope is visible. But when the number goes beyond a certain point, for example beyond 5 or beyond 2.5 to 10, similarly for the negative values as well, what happens is that the slope loses its, the slope becomes very flat. Slope becomes flat, meaning that your gradient, when you are trying to, with respect to the slope, when you are trying to calculate the loss, because the slope is flat, the gradient becomes flat. So the training would progress at all, right? So this is what the paper is meaning. Now let's come back here and say that to counter attack this effect, what they are doing is that they are dividing the dot product QKT by the dimension of the Q itself, query itself, a square root of the dimension. This is what is called the scale dot production, is the core of transformer. We need to understand this thing. Now this similar operation will be done for all other queries, making the final output of the weight also as a matrix. You can understand when the Q, K, V are of similar dimension, then this is going to produce a square matrix, because you are saying that what happens to word 1 with respect to word 1, 2, 3, 4. So what happens to word 1 with respect to, let's say, 1, 2, 3 and T. That's how the weights are measured, one with respect to the other. What happens to word 2 with respect to word 2 itself, and then word T. So naturally that becomes a matrix representation of the weight of one word with respect to the other word. Fine. This is important. We have to always understand the output of the self-attention becomes a matrix. Square, when we are trying to get the attention, self-attention for the words itself, but it may be different when it is an encoder decoder, then the source and the target word may be different. So, but nevertheless it is going to be a matrix. Okay, we take this weight now, this is the weight we are taking, and then we will apply this weight on V, right? That's how all our previous attention also worked in the similar manner. So what we are doing here is very simple. You drop this row here. If you drop this row, then what happens is multiply them by the weight, you are essentially seeing this weight alpha 11 is multiplied with B11, and this weight alpha 1t is multiplied with Bd. So this row is applying on this row. This row is also going to apply on the last row, which is Bt1 and all this. Instead of displaying it as a row, I am putting it horizontally. So this is the value coming from this row, and this one applied, multiplied on the last row is represented here, correct? Now you are going to sum them up because it is nothing but weighted average. So you are going to sum them up, and each sum is going to produce is the value here. This is the weighted value coming out like this, right? Now other weights will be applied similarly on this word. Again, that is going to produce a matrix. In the paper, it is represented in this manner. They start from Q just by saying the what is Q? Q is nothing but a linear projection of the actual word. We have expanded it in this manner. Q, embedded Q, linearly projected to generate the actual Q. So that is what is the Q, and then the K, which is this one, matrix multiplication, which we had done. Then this is scaled. Mask, optionally, we will spend quite a bit of time on understanding what mask means. Just hold on. Then submask is applied, and then we got this result here, which is shown here. Then we are coming, they are bringing V. This is the V. On the V, this is applied. These weights are applied. Again, matrix multiplication is what will be happening at this stage. Then finally producing this output of the scale dot product. Up to this, let us quickly go to the code and see how we have implemented this part. Okay, this is our self-attention class. We have built it from by inheriting the keras layer. Okay, and it is taking input as D model, like we said, is the D model. Then we have the dk, the output dimension, that is what we want, dv, output dimension for the value, and then there are certain switches parameter which we will explain later. Right now just focus building the self-attention. So as we know, what is your query key and value? They are keras dense network. We can see very well. This is nothing but dense, right? Come here now, and we can see that query is linearly projected, which is passed through the dense without any activation. Therefore, it is linear. Key and value, right? Query key value was exactly the way we had displayed on the PPT. Then score is nothing but a matrix multiplication. We remember between the query and the key, where input Q, input K, and input V is passed, and it is just multiplied. Query and key is matrix multiplication. Then this is where the scale dot product is happening, which means the score is divided by the square root of the dimension of query, right? Okay, and then this score is, we will come back here later. First you understand only the self-attention portion. So this output is now matrix multiplication of the attention weight and the value. This line here, in this line, the score is applied on softmax, and then the attention weight, which is we are coming from the softmax, is applied on the value. So we again repeat, this is the scaled score. This is where it is converted to weight. This is where we are doing the matrix multiplication with the value. Matches with the PPT exactly, right? And then you return the output. That's it. Now let's go back to testing of this score. Now how we are testing is initializing this with a D model of 512. dk and dv both are set to 64. Okay, and now we just pass on the data, which is query, key, and value. since this is a self-attention, at the encoder side we are passing all three as same, and then we straight away go what is the output looking like. We'll go there and we see that the output is 101 number of sequences. What we have, those number of sequences, each one of them is 64 dimension. How it came? It just came because the attention weight was a square matrix of 101 and 101. The B was, as we know, we passed 101 of D model size, which was 512 possibly, then that was converted to 64 dimension. That was the value, and this 101 and this 101 cancels out, and we get is 10164. One batch, I mean within the batch we are not taking a batch, one single instance, 10 in sequence, and then 64 is the attention weight. We want to come. So by doing this, what has been achieved so far? You see, by doing the self attention, the scale dot product self attention, what efficiency, what problem transformer wanted to solve, if you remember in our first video. In fact, even that the video before, which was about the CNN, we presented this table. That table was basically comparing what was the problem in recurrent neural network. When we apply attention along with recurrent neural network, what was the problem? And what was the problem even if we move it to the convolutional neuron? In both cases we found that there is a problem of sequential operation first of all, because where it grows along with the sequence, linearly it was growing, so it was big O of n. Here in the convolutional neural network we had a constant sequence of operation. Okay. However, when you go to complexity per layer, we observe that the dimension, the embedding dimension D was normally is much higher than what sequence you provide. For example, embedding dimension would be 512, and possibly yes, a sequence what you will give it to the transformer or a sequence to sequence model will be much smaller than 512, maybe 10 word at a time, or maybe 100 watt at a time. So the author argues that this D is much more important, and if you do a quadratic function of D, that is much more expensive than this sequence. So in self attention, what we did, you see, the D remained constant. D is this square has been removed here, but instead this has been moved to n, which means if it is a very large sequence, then we are running into a different problem. This is one of the problem of transformer. For very large sequence, it is the quadratic complexity. But the author argues that normally D will be the n will be much smaller than the D, therefore it is a improvement. This is a good complexity. When you go to the last one, which is maximum path, you remember what is the path. Path means that without any crossing any layer, any weights and biases, how can I directly do the calculation of the attention? So when you are doing a self attention, when you are doing neural let's say recurrent neural network, then as we know that we are passing layers, so we are crossing more weights and biases, correct? From one word to another word we are constantly moving, so that's why it is linearly increasing with the number of sequence. When you went to convolutional neural network, we saw that there is improvement, because as we stack the convolutional neural network, there are layers it is crossing, but it is also it is not linearly increasing, it is the logarithmic relationship. So therefore this is an improvement, but here it is a significant improvement. It remains constant. Even if the number of sequence increases, your understanding of one word relationship with the other remains constant, however large is the sequence. So these two plays major role in transformer in terms of getting the meaning of very large sequences. Here the computational complexity becomes larger, but the computational complexity is a matter of hardware, so these two are more important in this case. But the author also proposed something. For example, if it is really very large number, which is where n becomes much higher than D, which is, let's say, embedding dimension was 512 and you are trying to give sequences which is 1000 word long, in that case they are saying that break it up into windows. If you break it up in windows, then it is those many windows, then in is becoming linear, and all of them is not quadratic, you see, it is just RND. And R could be how much? If you are talking about 512 chunks, if you are talking about a 2000 or 4000 number of words and divided them into 512, then you are what we are talking about 6 to 8 number of R, right? R windows. And that's the window size. Then instead of constant complexity, the maximum path length, it will be n by r path, or n by r hop that one word has to cross to go to the other window and then get their correlations, right? That's what it is. So that's I think that's all about the self-attention. We are going to, in the next video, we are going to only focus on the masking that will complete the self-attention. In the masking, there are 3-4 aspects. We want to focus deeply there along with the codes. Otherwise, the self-attention coding is not complete, and we don't want to make this video too large. So see you in the next video and then explain on the masking part. Stay with me.